So we've been putting numbers into scientific notations ever since National 5, and we're quite happy doing it. And a number in scientific notation has times 10 to the power something, doesn't it? And that number, times 10 to the power whatever, is an order. And so if you compare the orders of two different numbers in scientific notation, what you're getting is you're getting a good indication of how much bigger that one number is than another. You are comparing the orders of magnitude. Magnitude means size. So for example, the diameter of a proton is 1.6 times 10 to the negative 15 meters. The diameter of our broth is 3 times 10 to the power 3 meters. Now we can just say 3, between 3 and between minus 15, that's 18 steps, isn't it? Think of a number line. So the diameter of our broth is 18 orders of magnitude bigger than the diameter of a proton. So think of a number line and just do the bigger number minus the smaller number. In this case it would be 3 minus 15, which is 3 plus 15, which is 18 orders of magnitude. The diameter of Earth is 12.8 times 10 to the 6 meters, so that is 3 orders of magnitude bigger than the diameter of our broth. The diameter of the Milky Way is 1 times 10 to the 21 meters. Well, if we're comparing the orders of magnitude between the diameter of Milky Way and the diameter of Earth, well, we're going from 6 up to 21, so that's a difference of 15. So think of a number line, really. We're not just doing this with units of length, we can think about time. So the time for an electron to orbit the nucleus once is 1 times 10 to the negative 18 seconds. The length of time which a human lifespan is about 2.4 times 10 to the negative 9. So think of a number line between negative 18 and plus 9. That is 27. And so we say the human lifespan is 27 orders of magnitude bigger than the time for an electron to orbit once. The time for a galactic year, so this is the time it takes for the galaxy to complete one full rotation, is 7 times 10 to the 15 seconds. So again, we could compare that amount of seconds with the seconds in a human life. So from 15 to 9, or 9 to 15, that's 6 orders of magnitude, isn't it? So the galactic year is 6 orders of magnitude greater than the lifespan of a human. So what's the point in this? Well, scientific notation gives us sensible numbers, even if we're dealing with very small things and very big things. And also this whole idea of comparing the orders of magnitude just by thinking of a number line and subtracting one from the next one. This allows a really quick and easy way to compare without necessarily having to get the calculator out. That said, if your mental maths is as hopeless as mine is, and you want to use a calculator for stuff like this, I don't know, 3 minus 15, so you know you're not going to make a mistake, please do that. But the theory is it allows a quick and easy comparison which you can more or less do in your head, and those are orders of magnitude. So the Doppler shift of waves. Imagine there's, I don't know, a little duckling in Kepty Pond, and the duckling is smacking the water with its feet or whatever, playing around, and it's creating ripples of water waves. And there you are on the side of Kepty Pond, and these water waves are coming at you at a regular rate, a regular frequency. So if this little duck then starts going off in a certain direction, then what you'll notice, if you stay in the same position, is that the frequency of the wave arrival, the frequency of arrival of the waves coming back at you, reduces. The time interval between each wave coming back to you gets longer and longer and longer, so the frequency is getting less. Well, if you think about a wave vibrating, if the frequency is getting less, then the wavelength is increasing. So if something's moving away from you, but if the source of waves is moving away from you, then the waves coming back to you, their arrival has a reduced frequency, they arrive with a reduced frequency, and an increased wavelength. If, however, you were in front of said duck and it was approaching you, then the frequency of wave arrival would actually go up. The frequency of wave arrival would increase. You have more waves arriving every second, and if you think about a wave vibrating, if the frequency is going up, then the wavelength gets smaller. So we've got a formula which can tell us exactly what the localized frequency is going to be at a particular location. So f subscript 0 is the observed frequency. It's the frequency where you are. And fs is the original frequency of wave emission. So this would be like the original frequency with which this little duckling is hitting the water with its feet as it paddles or whatever. And then this v divided by v plus or minus vs. V is the wave speed, and you get that on the data sheet. V underneath, that's the wave speed again, and then Vs is the speed of the moving thing itself, the object, the source of the wave. So in this case it would be the speed of the duck. Taking a step back, you can very much think of this as f subscript s being the original frequency, and then this stuff in this brackets being like a modification factor. So the original frequency, as emitted by the speeding thing, is modified by a certain amount, and as a result of that, what you observe, what you experience, is different. Maybe that helps, maybe it doesn't. You observe the original frequency, which has been modified a bit. People tend to mix up the different speeds. This is one of the awkward things about this. So v without anything is the wave speed, vs is the speed of the moving thing. Do you pick positive or do you pick negative? Well, if this thing is coming towards you, then you're gonna, so like if you're there, then you're gonna pick the negative version. If it's going away from you, like if you're that person there, you pick the positive version. With a cute little duck, it doesn't really matter if something's coming towards you, does it? You'll probably bend down, coo, and try and feed it bread. But if you imagine it's like a car coming towards you, then you could imagine that's going to be quite a negative experience, or a lorry or whatever. So if something comes towards you, you think of that as quite a negative experience, whereas if you've got a car or a lorry moving away from you, then that's going to be a more positive experience. So coming towards you is negative, going away from you is positive. Newton's law of gravitation. So imagine a ball rolling down a slope. If there was no friction, the ball would keep on going in a straight line at the same speed forever. And it's the same with the planets. Planets, if there was no force in space, the planet would keep on going in a straight line forever. But they don't. They orbit. Here's a picture of a planet orbiting a star. It's also the case with the Moon and the Earth. So there must be a force, and the force is gravity, and Newton's law of gravitation gives us a way of calculating this. So the gravitational force is the gravitational constant, big G, and that's on the data sheet, times the mass of the first object times the mass of the second object, all divided by the distance between the two centres squared. Now, because objects in space, the distance between them is quite often given in kilometres, people do tend to forget to change that to metres. So remember the prefix, kilo is times 10 to the power 3, don't forget to do that. And then people who remember to do that, they're so pleased that they've remembered to put it into metres, that they forget to square it. So don't forget to square it. Alright? Those are the common mistakes with that. This formula, and actually the previous one about Doppler, some people get a bit stressed with the maths. But do realise you get a mark for writing out the formula, you get a second mark for sticking the numbers in, And then even if the maths goes wrong, you've got 2 out of 3 marks. And that's especially the case with the Doppler formula on the previous slide. So even if your maths isn't great, and even if you think you're going to struggle with it, write down the formula, stick the numbers in. That doesn't need any maths whatsoever, and then you know that you've got 2 out of 3 marks regardless. You can give the maths a go. If it works, great, you get the final mark, but if it doesn't, you've still got 2 out of 3 marks. So, connected bodies. Bodies in physics just means objects. It's not like we've tied a bunch of bodies together and we're dragging them along. So this is probably best done with an example. So we've got 3 bodies, 300 kilograms, 300 kilograms, 200 kilograms, and there's a forwards force of 8,000 newtons on the first one, and this is dragging all of them along. But on each of these 3 objects, each of these 3 bodies, there's also 200 newtons of friction, and they're connected. And we want to calculate the tension in this particular connector here. So how do we do these things? Well, at higher physics, it's always a case that this connected system is accelerating. So what we do is we first of all need to find out the acceleration of the whole system. So if it's accelerating, we use the formula Fun equals ma, and we use Fun equals ma for the whole system to get the acceleration, and then we zoom in on the individual link we want. So we use Fun equals ma for the individual link we want. Okay, so we'll keep going with this example. So remember, we said to begin with we think about the whole system. So the mass of the whole system is 300 plus 300 plus 200, which is 800 kilograms. The overall force of the whole system is 8,000 minus 200 minus 200 minus 200. So 8,000 minus 600, which is 7,400. And we're trying to find A. Fun equals mass, stick the numbers in, and the acceleration of the system is 9.25 meters per second squared. So we found the acceleration of the whole system. And because everything's connected, the acceleration of each individual body is also going to be 9.25 meters per second. So now we've found the acceleration of the whole system, and therefore the acceleration of the bit in which we're interested. We zoom in on the bit which we're interested and do Fun equals ma again. So the bit which we're interested in is this bit, and the mass is 300, the acceleration is 9.25, and tension is what we're trying to find. The tension in a link depends on the mass that link is towing. So the mass which this link is towing is very clearly just 300. But if we had been asked to find the tension here, not there, but here, then the mass number we would have put in is 600, so 300 plus 300, because this connector here would be pulling a total of 600 kilograms. As the tension in a particular link depends on the total mass which that link is pulling. So if we were finding the tension in this link, it would be that much mass plus that mass. Whereas as it is, we're just finding the tension in this link, and it's just pulling 300 kilograms. So that's why I've got 300 kilograms. Anyway, Fun equals mass, stick the numbers in, answer comes out. Let's deal with slopes. We have a 5 kilogram box at rest on a slope.